Math 2414, integration by parts. Example 4, the recursive scenario. I'll explain what that means when the time is right. All right, let's take a look at this integral. The integral of e to the 2x cosine of 4x dx. Now, if you were really paying attention in the last video, when we integrated x squared e to the 2x, you'll have picked up on the fact that when one of your factors is a polynomial, it should be called u, because with enough repetitions of integration by parts, that polynomial would get differentiated into a constant, leaving the other part of the integrand ready to integrate on its own. If one factor of your polynomial, one factor of your integrand is a polynomial. But that's not the case here. E to the 2x is not a polynomial. Cosine of 4x is not a polynomial. Well, at least not finite polynomials, but that's not something we're going to visit in this class until chapter 8. But anyway, if we wanted to integrate this, this does not fit any of our integration rules, because we have rules for cosines, we've got rules for e's, but not rules for the products of the two. But the fact that it is a product suggests doing integration by parts. But how are we going to make our choices for u and dv? Our choices for dv are things that we can integrate, and honestly, I can integrate both of those as many times as I want. Cosine just alternates between cosine and sine, and watch your pluses and minuses. For e to the 2x, every time I integrated it, I would pick up another 1/2. See the previous video if you want to know what I mean, but it would be easily integrable. And both of them I could differentiate as much as I want. I would have to invoke the chain rule each time, but that's not a big deal. But neither of them is going to disappear if I say you're the u and take your derivative. So what would happen if we tried to do integration by parts? Well, let's just try it. First, we have to decide what to let u equal and what to let dv equal. And as I just mentioned, I can integrate both halves of this product, and I can differentiate both halves. So there doesn't seem to be a clear-cut choice as to which to let be the u and which to let be the dv. I'm going to choose dv to be the e to the 2x dx, namely because in the previous video we integrated that repeatedly, and the integral of that was 1/2 e to the 2x. If you want to see the details, go watch the previous video, but I'm going to take advantage of that in this one. That would leave u equal to cosine of 4x. All right, if we make these choices on how to partition the integrand into u and dv, let's see what would happen. Then du is equal to, well, derivative of cosine is negative sine, but the chain rule says leave the inside alone and then multiply times the derivative of the inside. So I'm going to pick up a 4. Let's go ahead and put it in front with a negative. You know, if you look ahead, it's like playing chess. If you look a couple of moves ahead, you can anticipate writing that negative 4 before you write the trig function. And the du picks up a dx. And for v, we would integrate e to the 2x, but again, we did that repeatedly in the previous video. It's still 1/2 e to the 2x. If you didn't watch the video, just think about taking this guy's derivative. Chain rule would pick up an extra 2, which would cancel the 1/2. So where does that put us? That puts us at the integral of e to the 2x cosine of 4x dx is equal to uv. So cosine 4x times 1/2 e to the 2x. Let's write that as 1/2 e to the 2x cosine of 4x minus the integral of v du. So minus the integral of v du. Well, let's be efficient. When I multiply these together, they'll be negative, but we'd be subtracting a negative, so it's going to become positive. If we multiply these together, the 4 times 1/2 makes a 2. And again, we have an exponential and a trig function, and since the precedent was established to put the exponential in front, let's stick with it. E to the 2x sine of 4x. Great, we're right back in the same situation we were at the beginning. We still have the exponential, we still have a trig function, it just happens to be sine. So are we just spinning our wheels? Well, it might look that way, but let's do integration by parts again. So IBP again. over there. Well, let's write this here. Integration by parts again. And no reason to change the decisions that we made before. Let's let dv be the e to the 2x. In fact, let's bring the 2 with it. 2e to the 2x dx. And let's let the u be sine of 4x. Why I chose to put the 2 with the e, I could have put it with the sine. It's just a constant. It's not going to change anything. Let's see what everything is. du would be the derivative of sine of 4x, which is 4 cosine of 4x. The 4 comes from the chain rule derivative of the inside. And, well, here we need to be a little bit careful for v. Without the 2, this would still be 1/2 e to the 2x. But times 2, it would just be this times 2. The 2 would cancel the 1/2 and leave an e to the 2x. So where does that put us in the whole problem? Remember, we're in the midst of this integration by parts while doing that one. So let's bring this piece down. 1/2 e to the 2x cosine of 4x. Plus, and now I can perform integration by parts on this integral. So let's start with u times v, which will be e to the 2x times sine 4x. E to the 2x sine of 4x. Minus the integral of v du. So minus the integral of e to the 2x times 4, oh, there's a dx here, sorry. If we put all this together, the cleanest version is going to be 4 e to the 2x cosine of 4x dx. And let me bring down the original integral, just to remind you where we started and where we are. Well, shoot, right back where we started, practically. We did the integral of e to the 2x cosine 4x, and I'm going to put some red boxes to kind of make this a little bit more readable. This was our first integration by parts. And when we did that, it took us to this integral, which invoked the second integration by parts. Second integration by parts. And when we did that in the first integration by parts, it took us here. But look at the integral we currently have. The 4 is a constant. I can pull that out. Let's just put it in front. I know I didn't do that before, but there's a reason I'm doing it now. Recognize that integral? Integral of e to the 2x cosine of 4x dx. Isn't it kind of the integral that we started with? This is why it's called the recursive scenario. The same expression is recurring again, which makes it seem like we can't do this problem, because if we did integration by parts a third time, we're just going to repeat this process and it will never end. So does that mean we're stuck? Well, not quite. Because think about what our goal is. Our goal is to know what this equals. There's actually 2 ways to figure out what something equals. Number 1, work it out, which we normally do. Number 2, find an equation that contains it and solve for it. If you'll notice, the thing that we want to solve for is here and here, and it's embedded in an equation, and we can just solve for it. When this recursive scenario happens, when you do integration by parts, usually twice, sometimes it's more than twice. I've seen a weird case where it's once. In fact, we'll see it later. But if you're doing integration by parts and you end up back at the integral that you started with, and there are things that survive because sometimes everything cancels, not in this case, then you can just solve for the integral. Not evaluate it, but solve for it like you're solving for a variable. Think of it this way. If I said solve A plus, if I said solve A equals 1/2 B plus 1/2 C minus 4A, and I said solve that for A, you would just add the 4A to both sides and then divide everything by 5, because you would pick up a 5 over there. Well, it's the same thing here. It's just that instead of A, we got a big chunky thing. That big chunky thing is this integral. So if I wanted to solve for it, I would start by adding 4 of these integrals to both sides. I'm going to bypass writing the actual moves because I'm running out of space. But if I added 4 of these integrals to this side, they would cancel. And if I added 4 of the integrals to this side, here's one of them, I would add 4 more to get a total of 5 of them. So I would have 5 of these integrals. Equal to that, the rest of this. And I think I'm going to go ahead and factor out an e to the 2x here, because I can. I'll get e to the 2x times 1/2 cosine of 4x plus sine of 4x. And now to solve for the integral, I just have to multiply both sides by 1/5. Therefore, the integral of e to the 2x cosine of 4x dx is equal to 1/5 e to the 2x times 1/2 cosine of 4x plus sine of 4x. And at this point, because it is an indefinite integral, now is a good time to pick up the plus c. We could have picked it up much earlier, but it would have been multiplied by 1/5 and just become a different constant. Or even if we picked it up here, we would have gotten multiplied by 4 and become yet another constant. But that's the crazy thing about constants and integrals. If you do arithmetic to a constant, it just becomes another constant. All right, so the recursive scenario occurs when neither part of your integrand would disappear upon integration, upon successive differentiations, and you end up, the integral that you're solving for recurs throughout the problem. Oh, we started with it and there it is again. But if you're lucky enough to get an equation that contains the integral you're trying to solve for, then you can just solve it algebraically. It happens. It doesn't happen all the time, but obviously it happened this time.